the Ball Game, sung by Edward Meeker, Edison Record.
All right, how you guys doing? I'm catching you here from on top of the Green Monster in Fenway Park, and we're going to talk about some solutions to special forms of linear systems and how that can be used to later sort of inform how we do bigger ones, okay? So in doing these special cases, the very first one that we can look at here, so I give you an equation, x prime equals negative x plus y, and y prime equals negative 3x minus 5y. Okay, and right now we don't know how to solve this. We kind of do if we're really clever, but we don't quite yet know how to solve this given what we've learned in class. But what we can do is just check solutions. And so I just want to go through this all, you know, that like it's a valid strategy for potentially like figuring problems out. And a lot of the way that we do things will come out this way. So if I tell you like x equals e to the negative 4t minus 3e to the negative 2t, and y equals negative 3e to the negative 4t plus 3e to the negative 2t, what are you going to do? Right? You're going to be like, okay, yes, of course, that makes total sense. Or you can check the work. So first things first, to verify, take the expression I gave you for x, take its derivative, because we're going to plug it in to basically this very first equation right here. Okay? So if we take the derivative of that, all right, we can see that we're just taking the derivative of these exponential functions. So we have negative 4e to the negative 4t plus 6e to the negative 2t. I've done all the respective work. Now, don't write an equal sign right now. Don't do it, okay? But write down negative x plus y, because that's what x prime is supposed to be. And then plug in the solutions I gave you for x and y into that expression right there. So we have negative e to the negative 4t plus 3e to the negative 2t minus, or plus negative, whatever, 3e to the negative 4t plus 3e to the negative 2t. All right, now when you do all the algebras involved in this here, well, first off, look at how we've got a 3 and a 3 in front of the negative e to the negative 2t. That's a 6. And then negative 1 and negative 3, that's a negative 4. Awesome. Those two things are the same, so that is a solution for x. Okay. We can do the exact same thing to verify that the solution I gave you is a solution to y by first taking its derivative to get 12e to the negative 4t minus 6e to the negative 2t. And then plugging it into the right-hand side, which is, I mean, a little bit uglier, but not much. We get negative 3e to the negative 4t plus 9e to the negative 2t. That's negative 3x. And then we get plus 15e to the negative 4t minus 15e to the negative 2t. That's minus 5y. Looking at those two together, 9 minus 15, that's negative 6. Negative 3 plus 15, that's 12. Awesome. Those are the exact same things. And what's cool is my solution here actually gives you a little bit more information because I don't have any constants in front of them. I actually gave you initial conditions that you can find by plugging 0 into my solution for x to get negative 2 and 0 into the solution I gave you for y to get 0. And so those right there would be the initial conditions that go with this problem for which that's an answer. Yay! Done. So that's not really like a technique that you can do, but it's something that you need to know what goes on. Okay. The next thing that we're going to talk about are so-called decoupled systems. Now, normally, like when I was talking about foxes and rabbits and the whatnot, we want x to influence y and y to influence x. We want them to be related. Okay. But in a decoupled sense, basically, neither of them actually influence one another. We just have two state variables and their rate of change. And you can see this because in the x equation, there's only x's. And in the y equation, there are only y's. So there's no actual interplay where they can influence the value of one another. We can solve both of these no problem because they're both separable differential equations. X of t equals the initial condition times e to the negative 2t, and y of t, which, whew, that green is horrible to write with, is the initial condition times e to the negative t. So we've got exponential decay of both of the state variables. Now, with systems, we've been thinking about that phase plane description, because I can write both of these as a function of time, no problem. But I want to think about x and that vertical axis, that's supposed to be y, that's a y. Okay, you pick an initial condition and you look, y is going to be decaying, but x is going to be decaying faster. So what we should have is a steeper slope in the horizontal direction than we do in the vertical direction that leads to 0, because the limit as t goes to infinity of both of these functions is 0. So no matter where I start, and I don't know how I made that straight line there, we just have this decay down into 0 where it's moving horizontally a bit faster than it's moving vertically. All right. Cool. Regardless of the initial condition you pick, That's what's going to happen. And this is a special case of things that we are going to be talking about more later. Now, in this sense right here, we've got a partially decoupled system. And so we don't just have x as a function of x and y as a function of y. There is some interaction. And what we can see here is that there's a y in the x prime equation. So that means y is influencing x. But since there's no x in the second equation, x does not influence y. So it's partially decoupled. What that means there is that y equation, we can solve that one all by itself. We don't need to know what x is. It just operates. So y equals the initial condition times e to the minus 4t. Now, what can we do with that piece of information? Because now I know that no matter what the time is, I know what the exact value of y is. So I might as well plug it up in here. It's not an unknown state variable anymore. It's a function of time. So that changes my equation to x prime equals 2x plus 3 y naught e to the negative 4t. A couple important things. You'll notice I didn't squish the 3 into the y naught, just call it a constant. Because I already know that that y naught's the initial condition, I don't want to erase that fact. Had I left this as just some k value and an unknown constant, then that 3 could have gone into the k, no problem, okay? But I know it, so let's not mess with it, all right? We know a couple different ways to solve equations like this. We can use integrating factors, which is the way that we learned, and that's 100% correct. Or I'm going to do kind of like this weird sort of hybrid thing because I like the linearity principle. I like finding the homogeneous solution and then a particular solution. And we can do that even though it's just first order, nothing changes. There's my associated homogeneous problem. And, well, the characteristic equation of that's just lambda minus 2. Oop, Nerd Cubed is live on Twitch. Go away, it did record that. So lambda equals 2. So my homogeneous solution is e to the 2t. Awesome, right? Now we can try to find a particular solution to this problem, correct? So for a particular solution, I'm going to guess some constant a times e to the negative 4t and plug it in to my full problem. Right, and so I'm going to get a negative 4a e to the negative 4t equals 2a e to the negative 4t plus 3y naught e to the negative 4t. What was taking so long? Keep writing. Keep writing. Low battery, go away. Keep writing. Okay, great. Everybody in that equation has an e to the negative 4t, so get rid of it. Let's go ahead and move the a over because a is what we want to solve for. A is that unknown coefficient that we're determining. So negative 6a equals 3y naught, which is a number. And so a equals negative 1/2 y naught. So that gives us a particular solution in this case of, so x of p equals, okay, k e to the 2t, this, I'm writing the general solution down, plus or minus 1/2 y naught e to the minus 4t. And that's my general solution because it's the general homogeneous equation solution plus my particular solution. And you'll see that the y naught is actually in my solution for x and my solution for y. But what you won't see in my solution for y is an x naught because y influences the value of x, but x does not influence the value of y. So it should show up there. And I don't know why I went to the next page, but whatever. That ends this. That can go away, god damn it. All right, I'm going to enjoy no baseball this season. Thank you, COVID-19. You guys have a good one. Where's the off button? Right over. Come on.